Hello everyone, and welcome to our presentation on One-Way ANOVA and multiple comparisons. Our team name is Team Vectors, and today we'll be guiding you through essentials of the statistical techniques and how it helps compare means across multiple groups. Let's dive right in. Here we have provided the contents for this presentation. Introduction, assumptions of One-Way ANOVA, hypothesis in One-Way ANOVA, conducting One-Way ANOVA in R, checking assumptions in R, multiple comparisons post-HOC test, conducting multiple comparisons in R, interpreting results, and lastly the conclusion. Let's start with the introduction. One-Way ANOVA or Analysis of Variance is a powerful statistical test used to compare the means of three or more independent groups. The main goal of this test is to determine if at least one of the group means significantly differs from the other. This test extends the two-sample t-test to more than two groups, making it more efficient and reducing the chances of making type errors, which can occur when performing multiple t-tests. For instance, let's say we want to test whether different types of fertilizers having varying effect on plant growth. In this case, we could apply One-Way ANOVA to see if the fertilizer types lead to significant differences in growth. Assumptions of One-Way ANOVA. Before we jump into the test itself, it's crucial to ensure that the assumptions for One-Way ANOVA are met. Firstly, we need independence, meaning the observations in each group should be independent of each other. Next is normality. The data in each group should follow a normal distribution. You can check this assumption using visual tools like histograms or QQ plots. Third, we have homogeneity of variances, which means that the variability within each group should be roughly equal. If this assumption is violated, we might consider using Welch's ANOVA as an alternative. It's important to note that if these assumptions aren't met, the results of your analysis may not be reliable. So it's vital to check them before proceeding. Now let's talk about hypotheses in One-Way ANOVA. In One-Way ANOVA, the null hypothesis H0 indicates that all group means are equal. In contrast, the alternative hypothesis H1 claims that at least one of the group means differ from the other. To determine which hypothesis we accept or reject, we compute the p-value. If the p-value is less than our significance level, typically 0.5, we reject the null hypothesis and conclude that at least one group mean is significantly different. However, One-Way ANOVA doesn't tell us which group means are different, only that there's difference somewhere. Conducting One-Way ANOVA in R. Now let's talk about the ANOVA formula. Let's take a look at math behind ANOVA. The F statistic is key value used to test the hypothesis. It's calculated by dividing the between group variation, indicated by SSB, by the within group variation, indicated by SSW. Mathematically, it looks like this. You can check the formula, which is on the screen, where MSB is the mean square between groups and MSW is the mean square within groups. If the calculated F value is greater than the critical value from the F distribution table, we reject the null hypothesis. The degree of freedom for both between and within groups are also important in calculating the F statistic. Now here we are checking the assumptions mathematically. To check the assumptions of normality and homogeneity of variances, we can use Statistical test. For normality, the Shapiro-Wilk test is commonly used. If the p-value is greater than 0.05, we can assume that the data are normally distributed. To test for the homogeneity of variances, we use Leven's test. If the p-value is greater than 0.05, it indicates that the variances across groups are equal, which is a key assumption for ANOVA. If the assumptions are violated, there are alternative methods available, such as the Kruskal-Wilks test, Wells ANOVA, that can handle violation of these assumptions. Let's dive in multiple comparisons. Post-HOC test. Now that we know ANOVA can tell us if significant differences exist, but not where it lies, we turn to post-HOC test. For further analysis, these tests help us to identify exactly which group means differ from each other. Common post-HOC test includes Tukey's HSD test, which is ideal for pairwise comparisons and assumes equal variances. Bone-Ferroni correction, which adjusts the significance level to prevent type errors when performing multiple comparisons. Dunet's test, which compare each treatment group to control group. For Tukey's HSD, we calculate the Q statistic, and if it exceeds a critical value from the studentized range distribution table, we conclude that the difference between those groups is statistically significant. Now let's interpret results mathematically. Once we have run the analysis, the next step is interpreting the result. If the p-value from the ANOVA test is less than 0.05, we reject the null hypothesis, meaning at least one group means differ. To assess the strength of differences, we can compute the effect size, which is often measured using ETA squared. Let's say we have three groups, which means 5, 6, 7 and pooled standard deviation of 1.2. We can compute the F static and compare it the critical value. If significant, we can then apply Tukey's HSD to determine which pair of group differs.
In summary, we will revise what we learned from this video. ANOVA stands for Analysis of Variance. ANOVA enables us to test for significance of difference among more than two sample means. There are two types of ANOVA, one-way and two-way ANOVA. On one-way ANOVA, there is one independent factor, and on two-way, there is more than one. We saw F distribution, which plays a crucial role in ANOVA. F test help us to decide whether the variance between group is significantly greater than the variance within group. We then looked at the ANOVA formula, ANOVA equal to variance between by variance within. If the variance between groups is significantly larger than the variance within group F value greater than 1, we reject the null hypothesis. If the variance between groups is not significantly different from the variance within group F value less than or is equals to 1, we fail to reject at 0, meaning there is no significant difference.
To conclude, one-way ANOVA is a powerful and widely used statistical tool for comparing the means of multiple groups. By ensuring the assumptions of normality, independence, and homogeneity of variances are met, we can confidently interpret the results. When ANOVA shows significant differences, post-HOC tests such as Tukey's HSD help pinpoint which groups differ from each other. By understanding how to compute the interpret the F statistic, effect sizes, and p-values, we can make data-driven decisions and draw valid conclusions. Remember, always check assumptions, interpret the results carefully, and visualize your data to gain deeper insights. Thank you for watching. If you have any suggestions and comments, you can directly comment down.